Hello everyone. In the previous lectures, we had been discussing various kinds of displacement potentials, namely the Helmholtz displacement potential, the Lami's strain potential, and in the previous lecture, the Galerkin vector potential. And in each of them, we had seen that in order to arrive at a convenient form of the ultimate governing differential equation, which was either in the form of a biharmonic equation or a set of biharmonic equations, or a uh, or a Laplace equation or a Poisson equation, we had to use the consideration that the body forces were zero. So suppose we do not want that. Suppose we do want to consider the influence of the body forces, and we do want to arrive at a representation which depends solely on the solution of Poisson equations. Then what? Well, as I have written down here, the kind of representation that we do in order to arrive at such a framework is the Papkovich-Neuber representation. And among all these displacement potentials that we have been discussing, this is the most modern one. Of course, please note that when I say that this is the most modern one, it is still around 85 to 90 years old. And nevertheless, it is widely used in a solution of in the solution of different kinds of elasticity problems in 3D elasticity, and we will illustrate the use of this to the solution of the Kelvin's problem. All right, so let me just state the motivation here clearly. It's twofold here: to include body forces and to uh, to set up the framework in the form of Poisson's equation, in the form of the Poisson equations. All right. Now, because this is something which you are actually going to use in the solution of problems, I believe it is going to be useful if instead of just the ultimate representation of the displacement vector in terms of the Papkovich-Neuber representation, I actually present to you the steps that are involved in order to arrive at that displacement potential. So this here already is a major difference from the route that we have been following in the previous displacement potentials, where I just wrote down the forms of the displacement potentials without actually going through any preliminary steps. So here we are going to discuss the preliminary steps involved in that representation of the displacement vector in terms of this Papkovich-Neuber representation. There is another motivation here, of course, that if you thought that in the previous lecture when we wrote down the Galerkin representation, if you thought, so let me just refer to that quickly. Okay, so back in our previous lecture on the Galerkin vector potential, if you thought that this particular form, this was quite complicated, and I mean the result of this was some kind of black magic, because it is not, you will probably think, if I just wrote down this Papkovich-Neuber representation, you will probably think that this is some kind of black magic, and not just some black magic but from an alien world. Okay, so in order to avoid that kind of any funny notions, let's actually go down to the details of it. So fair warning, first of all, that it will involve a little bit of algebra, quite a little bit of algebra. We have to resort to some clever tricks, but in the process of doing that, I hope you will be able to appreciate almost a mathematical artistry that is involved, or that was given by both these gentlemen, Papkovich and Neuber. Okay, so it's a good lesson to go through. All right, so without any further ado, let us get down to business. So the first starting point is to actually go back and refer to what was written down in the Helmholtz displacement potential. Okay, so we start out with uh, uh, so so we write that when the so that will be a starting point. Okay, you will see that it is not just a pure consequence of the Helmholtz displacement potential. Then ultimately there would not be any difference between the Helmholtz displacement potential and the Papkovich-Neuber representation. But in order to arrive at this representation, we start with this. Okay, there will be differences. There will be very important differences. So when the Helmholtz displacement potential was substituted in the Navier-Lamy equations, we had obtained the following. So let us look back to the Helmholtz displacement potential way back. So, so this is the form that I'm talking about. This one, this last step here. Okay. So uh, and please note that I am not going to consider this rho b equal to 0. Okay, I'm definitely going to include this because that is the motivation here. To include the influence of the body forces ultimately. Okay, so what we have is lambda plus twice g. Let me write that properly. Lambda plus twice g grad del square phi plus g curl of the Laplacian of the vector omega plus rho b is equal to 0. This is our starting point. Now before proceeding with anything else, uh, what we'll do is we'll simplify or rewrite this form in a certain way, uh, and you will see that, I mean, it may seem a little bit arbitrary to you at first, but the motivation is that the ultimate forms of the equations that we want to arrive at, they'll be nice and beautiful if we do these kinds of algebras beforehand. Okay, so please bear with bear with this with a little bit of patience. Okay, so what we do first of all is to write this as lambda plus twice g, this thing as so lambda is e nu divided by 1 plus nu, 1 minus twice nu, and this twice g will just keep it as it is. Okay, uh, this e by 1 plus nu, you note that uh, this is twice g. This e by 1 plus nu, that is twice g. So we basically have this, so that what we have here is this thing. As I mentioned, uh, initially it may seem all a little bit arbitrary, but just be a little bit patient here. Okay, so we want to work with this form. So if we substitute this back here, what we are going to obtain is this twice g, 1 minus nu, 1 minus by 1 minus twice nu, grad del squared phi plus g curl of the Laplacian of omega vector plus rho b vector is equal to 0. And what we want to write this as is, let me go to the next page actually. I'll just divide throughout by 1 minus or 2 into 1 minus nu. So from the previous page, what I have is g divided by 1 minus twice nu plus g divided by 2 into 1 minus nu. So this 2 into 1 minus nu comes from this numerator here, I have to write this properly also. This rho b vector divided by 2 into 1 minus nu is equal to 0. Alright, so here this thing can be put in a nicer form by noting that this here we have a Laplacian operator, and here also we have a Laplacian operator, and we can think of this Laplacian operator can be taken out of this curl, and here this Laplacian operator can be taken out of this gradient. Of course, these things that I'm saying rather arbitrarily, these can be formally proven, these identities, that when you have the gradient of the Laplacian of something, that is basically equivalent to the Laplacian of the gradient of that very thing. Similarly, the curl of the Laplacian of something is equal to the Laplacian of the curl of that very thing. All these can be formally proven. You can just do this as little exercises, but we are not going to go into all that right now. So I'm just going to rewrite this as the Laplacian of g into 1 minus twice nu grad of phi plus g divided by 2 into 1 minus nu curl of omega that is equal to minus rho b vector divided by 2 into 1 minus nu. Okay, now for apparently no rhyme or reason, we are going to set this to a variable, this entire thing sitting within this square bracket, as minus b vector. So first of all, you check that this phi here is a scalar quantity operated on by this gradient operator. This entire thing becomes a vector. Here the omega vector of course is a vector, the curl of a vector is another vector. So overall this first term here is a vector, the second term here is a vector. So overall this entire entity is a vector, and there is nothing wrong with writing this b vector. The only thing that seems quite off is that why are we doing this? You'll see the consequence of that. Okay, and just as a foreshadow of what it will ultimately turn out to be, this b vector is just one solid part of the Papkovich-Neuber representation. Okay, so as I said earlier that we are going to build it up with this starting from the Helmholtz displacement potential. So as a result of this rewriting, so when we said this, so let's write this down because this is an important thing. So we are basically setting b vector is equal to minus g divided by 1 minus twice nu grad of phi plus sorry about that, minus g divided by 2 into 1 minus nu curl of omega vector. So that's our b. So what we are basically obtaining is that okay, Laplacian of this entire b vector, that is equal to rho b vector divided by 2 into 1 minus nu. Okay, We'll put a box around this. Okay, this is one part of the Papkovich-Neuber representation, but the real some real mathematical artistry is just going to come after this. So first of all, you note that some of you may have a feeling that, okay, this does seem to be a reasonable representation. Okay, if you just look at our initial motivation, which was to arrive at a framework which would involve the force vector, which is the rho b here on the right hand side, and we also want to arrive at a framework which is like a Poisson equation. So this is definitely like that. It's a Poisson equation. Of course, it's a Poisson equation over a vector variable. So it seems our job is kind of done. But you see, there is a little bit of a problem here. The problem is, we have just set this variable, this entire thing is b. Now suppose one asks, all right, you can solve for this b vector. Can you find out the displacement vector from this? Well, in order to arrive at the displacement vector, you have to go back to this, to noting that ultimately we are proceeding from this step, and this phi and the omega, they are very much present within this b vector. So in order to arrive at the displacement vector u, you need to know what are the values of phi and this omega vector. But just by knowing the b vector, you cannot say what are phi and omega vector. So it is back to square one kind of thing. So what good does knowing b do us? Not much really. Okay, so we have to, so this is where, so the next part is where these difficulties are dealt with, and it is dealt with in such a clever fashion that you have to sit back and think about it a little bit closely and try to appreciate the mathematical artistry that is involved. Okay, that was so all great credit to the work done by Papkovich and Neuber. Okay, so how do we go about doing this? So as with any artistry, okay, so there is a stroke of genius involved. Okay, as with any great art, there's a stroke of genius involved, and that genius is to actually use a certain vector identity here. And again, it may seem rather arbitrary that we were talking about these displacement potentials. Suddenly, why are we going to use, I mean, out of the blue, a vector identity? Okay, and you see that vector identity is not something trivial. So the vector identity that I'm going to talk about, let me use this fresh page here. It goes something like this: del square x dot b vector, that is equal to x vector dotted with the Laplacian of the b vector plus twice of the divergence of the b vector. As I said, this seems like completely out of the blue. Why are we even using this? Okay. Furthermore, you should ask yourself, what is the proof of this? Okay. So the first part of that question, what is, why are we doing this? That will be clear as we proceed with the subsequent steps. And as I keep on saying, you will appreciate you should be able to appreciate the mathematical artistry involved. Regarding the proof, I could go into the proof of this in this page itself, but I'll resist the temptation of doing it and keep it for later, because if I go into that, it'll break the kind of break the flow of our development of the Papkovich-Neuber representation. So right now, just for now, you accept this vector identity in good faith, and I will come back to this later to prove this thing. It's not complicated. I mean, all of you can do this using the index notation, but nevertheless, I'll do this. Okay, so we're going to use this thing. So what we do is we write this like this. It just a little bit of a transposition. So x dot Laplacian of the b vector is equal to the Laplacian of x dot b vector minus twice divergence of the b vector. Now we are going to note a few things. First of all, if you go back to the previous page, you see that this del square b vector which is present here, we've already done this. Okay, we have already obtained this expression, so let's use this. Okay, so since del square b vector is this, the x dot del square b vector, this is equal to x dot rho b vector like this. Okay, I think it will be useful if I start numbering my equations. Okay, let's say that this is 1, this is 2, let's say this is 3. So what we are basically doing here is we are using 2. Please also note that this x vector that I am writing, this is the simple x vector representative of the coordinate system. Okay, so you have to note that just because I'm writing this as x vector, it does not mean that it is limited to the rectangular Cartesian coordinate system. Okay, this applies equally well to the cylindrical coordinate system, to the spherical coordinate system, and in those cases it will be corresponding to the r, theta, z, etc, etc. Okay, so this is just a generic representation. So we have something known about the left hand side of this equation number 3. Next, what about this this delta dot b vector? Okay, so for that we quickly refer to what we have in our equation number 1. Okay, so this equation number 1, it gives us an expression for the b vector. So if we take the divergence of this b vector, you please note that this first term here, the divergence of the gradient of phi, that will give me a Laplacian of phi, and this curl of omega, if I take the divergence of that, that is going to be equal to 0. Okay, so what we do is we say that delta dot b vector is simply minus g divided by 1 minus 2 nu Laplacian of phi, minus g divided by 1 minus twice nu Laplacian of phi, using 1 and the fact that the divergence of the curl of omega is equal to 0. All right. Now, if we substitute this back here in equation 3, okay, so let's say that this is our equation number 4 and this is equation number 5. So substituting 4 and 5 in 3, what we obtain is x dot rho b vector, this is in the left hand side, divided by 2 into 1 minus nu is equal to Laplacian of x dot b vector minus, so this thing, so there's a minus here, so overall this will be plus, this will be twice g Laplacian of phi divided by 1 minus twice nu. And from here we can easily obtain x dot rho b 2 into 1 divided by 2 into 1 minus nu, and we'll just take this, we'll consider this Laplacian operator in a common fashion, so that we obtain this as x dot b vector plus twice g phi 1 minus twice nu. Now if you're wondering that, if you're still wondering like why we are doing all this, I mean none of these steps are wrong, okay, none of these steps is wrong, but why are we doing all this? What is the motivation? See, we are still dealing with this b vector which we have artificially set, and we are still dealing with this phi. Where are we going with this? Well, what we do is we set this part as another variable, and here you note I have set it as a scalar variable, and that is consistent with the fact that this first term here is a dot product between two vectors, which is a scalar, and this here is a scalar quantity also. So overall this entire thing sitting within the square bracket is a scalar entity, and that I'm setting as beta, as minus beta. So we write this again properly, that we are setting beta as equal to minus x dot b x vector dotted with b vector minus twice g phi divided by 1 minus twice nu. So overall what we are getting is from this equation that Laplacian of beta is equal to minus x vector dotted with rho b vector divided by 2 into 1 minus nu. So what have we actually obtained? So just think for a moment. Okay, I'm trying to go through this as slowly as possible, so that you at least take some moments to realize what's going on, or at least to wonder why it is going on. Okay, or so previously we had boxed one equation. Okay, we had said that this equation number 2, that is one part of the Papkovich-Neuber representation, and it's kind of good that it satisfies our initial motivation of arriving at a framework which involves a Poisson equation. Now look back at getting back to the equation that we have just arrived at. On the right hand side you see this, here is a rho b vector. This is something which will be known to us in a particular problem. The x vector also will be known to us, because that is dependent just on the choice of the coordinate system. These are material properties. So is it not true that this here again is a Poisson equation where we intend to solve for this beta? Okay, so previously we had arrived at a Poisson equation involving the vector b Now we are arriving at another Poisson equation involving this vector, involving the scalar beta. So we box this equation. This will be another part of the Papkovich-Neuber representation. Okay, so let me number the equations. So the last equation that I had used was this 4 and 5. Let me set this as 6 and this as 7. So we note that both, so that the previous equation was equation number 2. So both equations 2 and 7 are Poisson equations satisfying the initial motivation. Now this kind of makes us happy, but you should not feel too happy right away, because note that it's great that we have found out two Poisson equations, but just because you can solve the Poisson equations based on the accumulated knowledge behind the history of these Poisson equations, or based on the history of these Poisson equations, what good does it do us? Are we actually able to solve our elasticity problem? What is the answer to that? Well, to answer that, you have to realize that your job is not yet done, because we have not yet connected the displacement vector, the u vector, in terms of this new variables b vector and beta. Unless that is done, our job is not done. Okay, we still have in our hand the u vector represented only and only in terms of our starting point, which was the Helmholtz displacement potential. That representation involved the phi and the capital omega. We have done a lot of algebra, we have done a lot of clever tricks, used vector identities and whatnot, and arrived at two Poisson equations involving the b vector and the beta. We solve that, and we find as our answers for beta and the b vector. So our next job will be to find out expression for the displacement vector in terms of that b vector and beta, and then only we can say that yes, we have a complete proper representation. So we start with what we know, which is the u vector in terms of the Helmholtz displacement potential, and try to see if we can rewrite this thing in terms of so let me write this again. This is the Helmholtz displacement potential. This was our starting point here. How is it possible to rewrite this in terms of the b vector and the beta vector? All right, so if we go back to our, what was, I think, our equation number 1, this is our b vector. So going back to equation 1, we have for our b vector minus g grad phi divided by 1 minus 2 nu minus g curl of the omega divided by 2 into 1 minus nu. Now from this equation, what we are going to do is we're going to use this curl of omega vector here from here. This is simply u vector minus grad of phi. So this is the part where you have to do a little bit of algebra. And you note that this can be further simplified a little bit. So we have this minus g grad phi common between this term and this term. So let's put this as plus. And within bracket we have minus 1 by 1 minus 2 nu plus 1 by 2 into 1 minus nu, and then we have this term minus g u vector divided by 2 into 1 minus nu. All right. Now what we are going to do is, see, our ultimate motivation here is to obtain an expression for u vector involving the b vector and the beta vector. I mean, from this step you can kind of see, if you can just overlook the messiness of this expression, we have kind of connected the u vector with the b vector, but this grad phi is still lingering here, so we'll have to take care of that. But we would like to rewrite this entire thing in terms of the u vector. So what I'll do is I'll divide or I will multiply throughout by 2 into 1 minus nu by g. Okay. If I do that and I transpose this to the left hand side, so I'm skipping a couple of steps. I hope you'll be able to follow along. So because I'm dividing by g, this term will go out, but I am multiplying by this 2 into 1 minus nu. So what I will obtain is this term grad of phi, and within bracket I will have 2 into 1 minus nu, 1 minus 2 nu. This one will become a 1, and this b vector term will go to the right hand side, but now this will be this will have a coefficient in the form of 2 into 1 minus nu divided by g. All right, let me simplify that a little bit. So this is minus 2 plus twice nu plus 1 minus twice nu divided by 1 minus twice nu minus twice 1 minus nu by g b vector so that u vector is, this twice nu cancels with this one. So overall what I have is minus 1 by 1 minus twice nu grad of phi minus 2 into 1 minus nu by g b vector. All right, I've done a little bit of simplification, but as far as the job of eliminating this grad phi, that is still left. So what do? Well, we want to bring into this representation of u uh, the beta. Okay, so the connection with b is done. Somehow you have to bring in the beta, and for that let me look back at what I have for my beta. Okay, so this looks promising because here I have an expression involving the beta, the b vector, which I don't mind having in my final expression, and there is a phi here. So possibly I can eliminate my phi from here. Okay, so I'm going to use this equation number 6. So going back to equation 6, I have beta is equal to, let me just look at that expression again, minus x dot x vector dot b vector minus x vector dot b vector minus twice g phi divided by 1 minus 2 nu minus twice g phi divided by 1 minus 2 nu. So see, what I need here is basically this grad phi term. Okay, so I have to take a gradient of this. Gradient of beta is equal to minus gradient of x dot b. I don't mind having this kind of a term present here. All that I care is to somehow eliminate this grad of phi. Alright, now this is looking promising because because you can see that this grad phi 1 minus 2 nu is very much present here. So what I can do here is I can write it like minus grad phi divided by 1 minus twice nu, that is going to be equal to 1 by twice g. So again I'm skipping a step here. So I'm dividing throughout by twice g, and I'm taking this to this side. So this one and this one will be on the same side. So gradient of beta plus gradient of x vector dotted with b vector. All right, so this entire thing I can substitute by this. So what I'll obtain in the next step, so let me number this equation also. So my last equation number was 7. Let's say this equation is equation 8, and this is equation 9. So substituting equation 9 in equation 8. What we obtain is u vector is equal to 1 by twice g, and please note that here I'll take this gradient operator common. So gradient of beta plus x vector dotted with b vector minus 2 into 1 minus nu divided by g b vector. And as a last neat step, I would like to take this 1 by twice g common, as I have been doing. So the motivation here is to just have this 1 by 2g factor outside, just like we had in the case of the Lami's-Strain potential as well as the Galerkin vector potential. So what we have overall is gradient of beta plus x vector dotted with b vector minus, so we have taken a twice g out of here, so this will become a 4 into 1 minus nu multiplied with the b vector. This is equation number 10. Now you see that previously we had obtained this equation number 7. We had also obtained this equation number 2, and now we are obtaining this equation number 10, which is basically our u vector. So let me put a box around this entire thing. Okay, so what we say is that this is the Papkovich-Neuber representation. Okay, so this is this here is the Papkovich-Neuber representation, where b vector and beta are given by equations 2 and 7. Okay, so this entire statement, this equation 10 together with equations 2 and 7, they constitute the entire Papkovich-Neuber representation. Equation 2 was one part, equation 7 was another part, and finally with this expression of the displacement vector in terms of the b vector and this b vector and the beta, together they constitute the Papkovich-Neuber representation. Okay, so of course it doesn't look as clean and neat as the previous displacement potentials, but please note very importantly, okay, all our initial motivations have been satisfied now. Why? Because both in equation number 7 here, okay, in equation number 7 we have the presence of the body force term. This is a Poisson equation. This Poisson equation can be solved. We have the means, the mathematical means to solve this Poisson equation. We also have this equation number 2, which again has this influence of the rho b vector very much present here. This is again a Poisson equation. We can very much solve it. So nowhere we have neglected the body forces, and the final representation may look a little bit complicated, but ultimately once you have the solutions for b vector and the beta, you just have to substitute it here and your solution for the desired displacement vector will come out. And the moment you have this thing, the displacement vector, you can go on to find out the strains, you can go on to find out the stresses, and your entire solution is done. Okay, of course when we have to apply this method for specific problems, there will be inherent challenges to it, but overall this Papkovich-Neuber representation has been studied in a proper mathematical way, and I mean there's a lot, there are a number of good properties associated with the Papkovich-Neuber representation. Of course we are not going to go into all those details. So what remains? Okay, what remains? So one thing which may be bothering you a little bit is that we have not yet done the proof for this thing. We have not yet done the so where was it? We have not yet done the proof for this equation number 3, or equivalently this one. Okay, so what I will do is in a separate lecture I will just put out the proof of this. I mean it's a rather short proof, so let me not prolong this particular lecture anymore, and on that note let me end this. All right, thank you very much.